Okay, so thank you very much for putting this event together. And of course, special thanks to AMD for hosting it. I would wish we would have something similar in Europe. I'm speaking to you from Berlin actually right now. It's somewhat dark outside, but happy to be here virtually nonetheless. So I am pleased to talk to you today about how we are dealing with expressing complex ONNX graphs with Spox and ndonnx. Now, the astute reader might realize that the title of this graph has slightly changed from what used to be large feature engineering pipelines to complex ONNX graphs. Now, there are two reasons. So the first is large feature engineering pipelines is longer and it creates an ugly page break and can't have that. The second and probably more important one is that large is just a bit ambiguous. So large could, of course, be, are we talking about megabytes? Does the graph has like large tensors? Or is it large because in terms of number of nodes, but not necessarily in terms of number of megabytes on disk? And it's actually the latter that I want to talk about. So at Quantco, we are oftentimes dealing with tabular data. We are working a lot in the insurance space. One might say it's somewhat traditional ML. So our setting is often that we have large feature engineering pipelines where we get data in all sorts of formats, and then well, we transform it, we throw it at various component models, like order of magnitude, like 20 maybe, and then we combine these models through various traps into a final prediction. And our goal really is to actually express this entire pipeline end to end, like from really the data comes in from a request on some API to the final prediction, everything in ONNX, including the feature engineering. And then actually in practice, we end up with graphs that have more than 10,000 nodes as a sort of roundabout number. So very large, complex graphs, but technically in terms of megabytes, they are not very big, like maybe 20, 30 megabytes. And now showing a graph with 10,000 nodes, of course, would not be very helpful on a particular slide. So I made a little like toy model just to drive home this particular toy. So this is really just a bunch of like large GBM regressors with like a very small toy feature engineering pipeline in the front, and then sort of combining the results into something final. And what I really want to sort of stress is while defining this graph, so we want to, like these graphs are essentially created at every time anybody, including clients who use our services, train a model, and then we essentially automatically create these ONNX graphs that sort of are associated with it. So we really want to have like this conversion to be really stable. If something goes wrong, we want to have like an easy to debug error. We want people to be able to fix it, etc. And what sort of comes with the stability is really if we, can you see my mouse?
Yeah, we can see your cursor here, but not when you're in presentation mode.
Ah, okay. Well,
yes.
Okay, then I'm pointing somewhere at the bottom left of the mouse of the graph. If you're defining something at the bottom left of the graph, clearly you don't want to deal with something that is sort of a completely different part of the graph. You don't want to care about like the naming of individual edges. You just really want to sort of define your application logic. Now, doing this in NumPy and SciPy is, well, pretty straightforward. I mean, for that matter, actually, this little toy example here is defined in a scikit-learn like pipeline. And the usability, the debuggability is really, really clear. And the question is, can we actually have something like that in ONNX? Now, I realize there are a bunch of contenders in this space, but we have invested quite heavily in the tooling actually over the last 2 years, primarily because we were not quite satisfied with the tooling that was available at the time in particular. And so let's dive in how we actually define these very, very large graphs. You get a really good developer experience with it. And rather than I am going to do a little bit of a semi-live demo as people with a Jupyter notebook. Here we go. You see my notebook?
Yep.
I did. As a yes. Okay. So let's take as a first case study, let's take NumPy. Of course, in NumPy, things are actually pretty straightforward to define. We just have a simple function. Let's just, for the sake of it, of course, this is not a large and feature engineering pipeline, but let's just say we want to add and scale something in NumPy. It takes an array as input, and then some arbitrary Python numbers, and we return an array again. We can branch on any value we like, and we get an array back. And of course, we can run this, and everything works well. Now, if we say we pass in a string here, then of course we get an error, and the error points us immediately, oh, okay, scaling is a string. It doesn't make a lot of sense to scale by a string. Points us exactly where the error happens, and everything is easy to debug. We want to have something similar with ONNX. So really, this is, well, just to sort of recapitulate the lessons. This is concise and plain Python. There is no AST parsing. We can put like a debugger statement anywhere we want to. We can investigate like what are the shapes, what are the data types of the arrays involved, etc., etc. Very debuggable, very nice developer experience. I guess that's why NumPy is so successful. So how would this exact logic look like in ONNX with the Spox framework? So similar to NumPy, we import first a particular namespace. In ONNX, of course, I mean, ONNX at the end of it is just a array, an API of tensor operations, and they are versioned by number. So we import, in this particular case, we import the opset version 20 as op, and just for typing purposes, we import this var object. So var objects are really just lazy variables. So rather than passing around arrays, we pass around these lazy variables. And we define a function that actually looks very, very similar. Takes a lazy variable, in this particular case, probably a tensor, and again, some arbitrary Python object returns a variable. And we can really branch on everything. And there is, again, no magic. It's just plain old Python code. We get a variable in, we branch as we please, we maybe add something, we maybe multiply something, and we get something out. So we would call it, in this particular case, we just call it with a constant. I'll get back to that in a second. And it just works. So we pass in a constant into this function. The Python function just executes. We get an array back of shape, one-dimensional shape 3 with these values. So there's actually constant propagation going on. Now, of course, the astute listener will immediately realize, like, hey, wait a minute. We don't really want to define graphs which sort of just take constant as inputs. We really want to define graphs that have like undefined inputs at the time when we actually create this graph. And of course, now the question is, how would we actually build such a graph? And we do that essentially by sort of marking where does the very first var object come from. In Spox land, we call it an argument to the, like, as an argument to a function, if you like. And we created using this constructor function called argument. We need to give it a particular type. It could be a map, it could be a sequence, etc. But we care about tensor, but Spox would support other types as well. And I will talk about build in a moment. But first, let's create this very first input var, or argument var. So it's an argument, an input to the graph of type tensor with data type float64, one-dimensional with length n. We get this guy, and it sort of just sits here. And now we just can use our function here. Again, no magic, just plain Python. We throw it through, and it sort of just executes. We see, oh, okay, there was some multiplication happening to it last time. It did see something, and it still has the same shape. So the way it works, like these vars, they just remember the ancestry, and then we can trace it back essentially at the time when we actually want to build the final model proto. So we have our build function. The build function takes inputs and outputs. We give them names here through the Python dictionaries. So X is our input, result is our output. We just defined it here. We create it, and we get a model proto as we would expect. So yeah, not the most picturesque maybe, but we see our output are here, the result. Input is here X, and in between we, for example, had our, for example, add nodes. Yeah, here was, for example, the addition happening, etc. So all the nodes made it into the graph. Very easy, very idiomatic. Now the problem is, of course, if we sort of look at this, we are like firmly in the land of just duplicating our logic. So we had our original feature engineering defined in NumPy. This is where we actually trained our models, etc. And now we actually duplicated this code and wrote the entire logic again in Spox. Now that's obviously not good. And earlier today, you actually heard a talk by my colleague Aditya Goel about a framework called ndonnx, which essentially allows us to get like very nice code reuse. How does it do it? So I defer to the talk in the morning about more details. But while Spox and NumPy really have these different APIs, that's why we have two different functions. NumPy version 2 at least actually follows the so-called array API, which is a project in the numerical Python space to essentially define an API that different backends can implement so that functions can just be transparently reused. And ndonnx is a framework that implements the array API, just like NumPy 2. So how would that look like? Now, if we sort of define an add and scale generic function against the array API, actually, this is just a copy of the NumPy function, but we can sort of, just for the sake of it, we define it. And now we can run this particular function here really with NumPy code. We pass it a NumPy array, works as expected, or we pass it an ndonnx array, which follows exactly the same API as NumPy, or at least like exactly the array API as NumPy, and that works as well. And from here, we can really just build graphs just as we did with Spox, except that we sort of use this higher level API provided by ndonnx, so we don't have control anymore about the opposite version, for example, but we get this very nice code reusability. And here we now build this graph, for instance, using exactly the code that we actually just reused, that we just defined for NumPy. Those are the very same code. There is no converter needed anymore. And the nice thing about this really is that scikit-learn is starting to adopt the array API. Well, actually, let me get back to my slides. So live demo done for now. So yeah. So yeah. So this array API actually it has gotten some good traction. I mean, it came from the NumPy people, from the SciPy people. It's being adapted in scikit-learn, and more classes in scikit-learn are actually converted. So it really means that we don't need converter code anymore. So to recap this very brief talk, so ONNX, I really like to think about it. Really, ONNX is just a tensor library API, and then the backends, of course, which also defines the semantic of each operator. And ONNX just is like an API defining various functions that pass tensors, get tensors as input and produce tensor output. And then Spox really is a library that in a very Pythonic way, no magic, super easy to debug, no surprises, just exposes what ONNX defines in a Pythonic and stable way. We use it since 2.5 years in production in our major projects. And it's just this very solid framework for further abstractions, such as ndonnx. So Spox is really the library to write converter libraries in. It's not a converter library by in itself. However, given that the array API is sort of on the rise, we get this very beautiful code reuse. And I'm very excited actually about the future, where libraries like scikit-learn just are written against the array API, and that will just diminish the code for the need for converters. There will remain to be a need for like some special cases, like for example, boosted decision trees, etc. They will still need custom converters to map to custom operators in the ONNX standard. But all in all, we will get more and more code reuse, I'm sure, and it will diminish the need for actually explicit converter libraries, which I think is just awesome. And now, of course, I realize this was a whirlwind of a presentation, very brief, but the two libraries that I just showcased, Spox and ndonnx, they are open source. ndonnx very recently. They have beautiful documentation, if I may say so myself, and give them a look. And I believe actually they're very user-friendly. And well, I'm using them every day and I'm actually pretty happy with it. Now, enough of this advertisement for open source libraries. Are there any questions if there's time remaining?
Thanks. Very cool libraries. You mentioned the ndonnx, does not expose offset to users. And I previously also learned from, I think, the talk from Aditya that you can interrupt ndonnx with Spox. So I was wondering if you do any reconciliation of offsets when you explicitly import offset from Spox, or do you kind of raise an error if they are incompatible, etc.?
No, not at all. Not at all. So actually, okay, there's a little bit of an echo, but let's take a look here at the example. So here we import from version 20. But in our case, we really define converters in various libraries. So some of them are in our core proprietary libraries. Some of them are defined upstream, downstream on the client side, and some others elsewhere yet again. So there would be absolutely no way to actually get everybody on the same version. But fortunately, actually, the ONNX Python library actually has some node adaptation where we can walk. So essentially, we build a graph where rather than the entire graph having one particular version, every node that, for example, the add node that is being created here behind the scenes, every node has a particular version. But then when, of course, we want to build a standard compliant graph, we adapt every version to the highest common denominator. So it's sort of, you can mix and match offset versions as you like. Well, it's a best effort, but so far we have not run into problems because actually ONNX upstream actually supports upgrading operators from old to new offsets pretty well. So bottom line, use the it's always good to use the latest offset, but you can mix and match as you like. And when you actually build the graph, the highest used version is being used for the final graph.
Makes a lot of sense. Thanks.